Bismillahirrahmanirrahim. Assalamualaikum to our Engineering Laboratory 2 Material Science lecturer, Puan Hafsa binti Muhammad Noor. Welcome to our presentation video. In this video, we will present the first material science experiment, the atomic arrangement in the solid structure and crystal structure. Before we get started, let me introduce myself as the first presenter. My name is Akram Shafaznil bin Azrin with matric number AA200543. I will explain the theory and objectives of this experiment. In solid materials, the physical structure depends on the arrangement of the atom, ion or molecules which make up the solid and the bonding forces between them. In general, types of solid material can be classified according to the atomic and ionic arrangements in the material structure, either amorphous or crystal. In this explanation, there is several cubic structure to be discussed. First is the simple cubic structure. There is only one lattice point at each corner of the cube-shaped unit cell. Polonium Po is reported to crystallize in simple cubic structure. Next is base-centered cubic unit cell. BCC has atoms at each of the 8 corners of a cube plus 1 atom in the center of the cube. The BCC structure is often the high temperature form of metals that are close packed at lower temperatures. Metals which have a BCC structure are usually harder and less malleable than close packed metals such as gold. Other than that, there is also face-centered cubic structure. The FCC unit cells consist of a net total of 4 atoms, 8 from the corner atoms and 6 halves of the face atoms. Some of the metals that have FCC structure include aluminium, copper, lead, iridium, nickel, platinum, and silver. Lastly is the hexagonal close-packed structure. There are 6 nearest neighbors in the same close-packed layer, 3 in the layer above and 3 in the layer below. The HCP structure is very common for elemental metals, and some examples include beryllium, cadmium, magnesium, titanium, zinc, and zirconium.
Hi, Assalamualaikum. My name is Anazakwan bin Tandiku. My matrix number AA200445. The apparatus, first one is stick. Stick is used to make the shape of unit cell geometries and to support the model. Second one is plasticine. Plasticine represent atom of unit cell. Procedure, first one is simple cubic. Make 8 ball shape using plasticine. Stick 4 ball in square array using toothpick. Repeat step 2. Combine 2 square array to become cubic shape. Second one is base center cubic. Make 9 ball shape using plasticine. Make 2 side of plane in square array by sticking the plasticine ball with toothpick. Combine 2 plane become cubic shape. Stick 1 ball at the center of the cubic model using toothpick to support the plasticine ball. The third one is face center cubic. Make 14 ball shape using plasticine. Construct 2 close packed planes using 6 balls, each by sticking the ball using toothpick. Join these 2 planes, rotating them slightly to fit in interstitial position. Attach remaining 2 plasticine balls to this structure at suitable positions. Last one is hexagonal close pack. Make 17 ball shape using plasticine. Stick 6 ball in hexagonal array and place 1 ball in the center hexagonal array. Repeat step 2. Stick another 3 ball in triangle array. Place the triangle array between the 2 hexagonal layer.
Assalamualaikum, my name is Ahmad Firas Firdaus bin Ahmad Zaki. My matrix number is AA200964. Okay, so I will continue for the results and observation. From this laboratory, we obtain the 4 types of unit cells geometry, which is the simple cubic, base-centered cubic, face-centered cubic, and the hexagonal closed-packed structure. As you can see in the slide, this is the photos of the results from our lab experiment. So for the observation, firstly for the simple cubic, we observe that it has a number of atom unit cells of 2. The arrangement is square array and it has 8 lattice points. So next, for the BCC or base-centered cubic, it has 4 atom unit cells and the arrangement is square array. And lastly, it has 9 lattice points, which is in the middle and 8 in the corners, each corners. For the face-centered cubic, the atom unit cells is 2 and the arrangement is square array. It's like a cube form of arrangement. And lastly, it has 14 lattice points, which is 1 in each of the face. So it has 6 lattice points on the face, and then plus 8 at every corner. Next up, for the hexagonal closed-packed structure, it has 6 atom unit cells and the arrangement is hexagonal array, which is the top of the structure is shaped like a hexagon, and it has 17 lattice points, which is 3 in the center and then 12 plus 2 at the top.
Hi, my name is Amir Hazim bin Azmi with matric number AA200257. Now I will explain about discussion of this topic. First, the difference between 4 unit cell geometries. First, number of atom per unit cell. For simple cubic, it had 1, base-centered cubic, it had 2, face-centered cubic had 4, and hexagonal closed-packed structure had 6. For the coordination number, simple cubic had 6, base-centered cubic had 8, face-centered cubic and hexagonal closed-packed structure had 12. For the percentage space, simple cubic had 52%, base-centered cubic had 68%, face-centered cubic and hexagonal closed-packed structure had 74%. Second, we can define void as gaps between the segments of particle. Second, in solid state means the constituent particle had vacant space between particle in closed-packed structure. Finally, it had 2 types of voids, is tetrahedral and octahedral voids. Take the calculation of the atomic packing factor. First, simple cubic. To find the atomic packing factor, we divide 4/3 pi r power of 3 by 8 r power of 3. So we get 52% of unit cell packed with atom. B, base-centered cubic. So we divide 2 multiplied by 4/3 pi r power of 3 by 4r over square root 2 power of 3. So we get 68% of unit cell packed with atom. C, face-centered cubic. To find the atomic packing factor, we divide 16/3 pi r power of 3 by 4r over square root 2 power of 3. So we get 74% of unit cell packed with atom. Finally, for the hexagonal closed-packed structure, we divide 6 multiplied by 4/3 pi r power of 3 by 24 square root 2 multiplied by r power of 3. So we get 74% of unit cell packed with atom. Finally, for number 4, the arrangement of 3 set square arrays is like in this example of image. For B, void percentage of the atomic arrangement can be found using void space equation. That is, void space equal to 1 minus atomic packing factor multiplied by 100. So we using this equation, we get simple cubic 48%, face-centered cubic 26%, body-centered cubic 32%. So we get total void space is 106%. Finally, for the conclusion, we can conclude that in atomic arrangement, each material had its own crystal structure that show material properties, and it had 40 types of unit cell geometry in Bravais unit cell. Each structure had its own coordination number of atoms in unit cell that can determine the atomic packing factor. So, that's all from us. Thank you.